That yellow tire pressure symbol may be reporting a measurement your car never made. Under the federal rule, the headline warning threshold is 25% below the pressure on the car's placard. In one kind of system, a sensor sealed inside the wheel measures the air directly and radios the result to the car. In another, there may be no pressure sensor in the wheel at all. The car watches how the tires rotate and infers that something changed. Both systems can light the same symbol, even though one measured pressure and the other solved a moving puzzle. So what does that light actually know, and why can a cold morning make it appear and disappear? The answer begins with the number most drivers never see. It is 25%. The pressure printed on the tire's sidewall is not the target for your car. The recommended cold pressure is on the driver's door jamb placard or in the owner's manual. Federal rules then measure the warning system against that placard value. Take a hypothetical car labeled 35 PSI. 25% below that is 26.25 PSI, so the legal warning line can sit far below the pressure the driver should maintain. The exact activation point can be higher, and manufacturers can warn earlier. But the federal system is a safety net, not a precision maintenance reminder. That distinction has applied broadly since model year 2008, when passenger cars, light trucks, and vans were required to carry TPMS. The lamp tells you that pressure is significantly low. It does not tell you that every tire above the warning line is correctly inflated. A direct system begins inside the pressurized cavity. A compact module, often attached to the valve or mounted on the wheel, senses pressure. Many modules also sense temperature. Electronics encode the reading with an identifier and transmit it by radio. A receiver passes that message to the vehicle controller, which decides whether to show a pressure value, illuminate the warning lamp, or report a fault. The engineering details vary by manufacturer, but the information path is consistent. It runs from tire to sensor, radio, controller, and dashboard. That path explains why some cars can show a separate PSI reading for each tire. It also explains why a direct system adds hardware that an indirect system does not need. There is no ordinary wire running from a rotating wheel to the dashboard, so the radio link is not a convenience. It is the bridge across a moving mechanical boundary. The wheel now contains an electronic device that must survive vibration, moisture, tire service, temperature swings, and years of rotation. Receiving a radio packet is only half the job. The car may also need to know which wheel sent it. Direct sensors carry identifiers, and the vehicle keeps a learned relationship between those identifiers and its wheel positions. Rotate the tires, replace a sensor, install another wheel set, or bring an incompatible component into the system, and that relationship may need to be relearned. Some vehicles perform the process automatically. Others require a sequence described in the owner's manual or service information. The dashboard also separates low pressure from a system failure. On vehicles covered by the current federal rule, a malfunction can make the lamp flash for 60 to 90 seconds and then remain illuminated. A steady low pressure warning and a flashing then steady malfunction are therefore two different messages drawn with nearly the same symbol. An indirect system removes the pressure transmitter from the wheel. It reuses signals the car already needs for systems such as anti-lock braking. When inflation falls, a tire deforms more under the vehicle's load. Its effective rolling behavior changes, and a simple version of the idea compares how quickly the wheels turn over the same trip. A wheel that behaves as if its rolling radius became smaller tends to accumulate rotations differently from its neighbors. The controller does not convert one wheel speed pulse into a trustworthy PSI reading. It watches patterns, filters normal driving behavior, and asks whether the differences resemble pressure loss. More advanced indirect methods can also use the tire's vibration or resonance behavior. The useful signal is therefore not a cartoon equation where one extra revolution equals one missing pound of air. It is a small behavioral change interpreted in context. That is the central trick. The car measures motion very precisely, then uses tire physics to infer a pressure problem it never sensed directly. Wheel speed changes for many reasons that have nothing to do with a leak. In a turn, the outside wheels travel farther than the inside wheels. Replacement tires can differ slightly in diameter. Tread wear, vehicle load, acceleration, road surface, and calibration can all change the signals. So an indirect system cannot treat every mismatch as a flat tire. It compares wheels, observes behavior over time, rejects driving conditions that would mislead the calculation, and relies on a calibrated baseline. The driver is not telling the car what the exact PSI is. The driver is telling the algorithm, in effect, that this is the new normal pattern. This is why a vehicle's calibration or reset step matters after pressures are corrected. The sophistication also explains why indirect TPMS varies so much between vehicles. A basic circumference comparison and a newer resonance-based system may share one dashboard symbol, while reasoning from different features of the same tire. Now consider a tire that is already close to the warning line. As the air inside gets colder, its pressure falls. An industry rule of thumb is roughly 1 to 2 PSI for every 10° Fahrenheit drop, although the real change depends on the tire and conditions. That can push a marginal tire across the vehicle's threshold overnight. After driving, the tire warms, pressure rises, and the lamp may switch off. NHTSA specifically warns that this on and off pattern can happen on cold mornings. The air did not repair a puncture, and the car did not contradict itself. The measured or inferred condition crossed a threshold in one direction, then crossed back. Temperature can explain the timing of the warning, but it does not prove that the tire has no leak. The warning lamp is deliberately simple, but the condition behind it is not. A direct system may no pressure yet have a dead or missing transmitter. An indirect system may have healthy wheel sensors, yet need calibration. Either system can warn late relative to ordinary maintenance, because the federal threshold allows a tire to become significantly underinflated first. That is why NHTSA still recommends checking every tire with an accurate gauge at least once a month when the tires are cold. In this guidance, cold means the car has been parked for at least 3 hours. Use the pressure on the vehicle placard, not the maximum molded into the tire sidewall. The lamp is a safety alert. The gauge is the measurement. And the owner's manual is the authority on how your particular car identifies, resets, and reports its system. That division of responsibility is the real design. Automation catches a dangerous condition, while routine measurement keeps the tires from reaching that condition in the first place. So the next time that symbol appears, remember what may be happening behind it. One car is hearing an electronic pressure sensor inside the tire. Another is watching wheel motion and recognizing a pattern. Both are warning systems, not permission to ignore the gauge until the dashboard complains. Check the placard, measure the tires cold, and treat a flashing lamp as a system fault rather than another pressure reading. If this changed how you see an ordinary dashboard light, subscribe to Yapnetic. We uncover the hidden engineering inside the things you use every day.